Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And it's about regular symbolic analysis for a model for multi-threaded programs we call dynamic network of pushdown systems. Okay, so as you know, program verification has several sources of complexity, and some of them are listed here. For instance, you have to deal with the data parameters over infinite domains. You have also to consider the fact that programs may manipulate data structures and have dynamic memory management. And also you have the control structure itself, which may be complex because you can have several features like procedure calls, dynamic creation of processes, and so on. So to deal adequately with these aspects, we need, in fact, to reason about infinite state systems because of this different aspect, the fact that you have infinite domains, you have unbounded memory, and you have also unboundedness here coming from the procedure calls and the dynamic creation of processes. So in this talk, in fact, I will talk only about the last aspect, and I consider that these ones, for instance, we have already done some abstraction of things like that, and we concentrate on these aspects. So the issue we have to address are here. For instance, we have to start by defining adequate abstract models, which allows you to reason about the aspects you are interested in. And here you have a variety of abstract models, such as pushdown systems and process rewrite system and so on. And then we are interested in looking at problems of decidability and the complexity for these models. And basically, we are interested in looking at reachability analysis. And then when the problems are not decidable in general, so we are looking for generic algorithmic verification approach, which allows you to deal with general models. So these algorithmic approaches are, so in what we are doing, are based basically on automata. So here, the models we are dealing with are based on extended automata, like pushdown systems and so on. And here we use automata as symbolic representations for sets of configurations. And then we want to apply techniques on this automata, which allows you to compute either exactly or in some approximate way the set of reachable states, and also in some case to perform model checking. So in this talk, I will present a model based on the networks of pushdown systems. And I'm interested in reachability analysis, and I will show you different techniques based on word or tree automata. Okay, so let me start slowly by showing which kind of models we are interested in. So pushdown system, I think that's, I think all of you know this kind of models. So pushdown system is very basic model where you have rewrite rules of this form. So you have control states, so you can go from P to P prime and modify the top of the stack gamma by some word W. And this is a prefix rewrite rule because you rewrite only the top of the word. And so this is the usual semantics. And these models have been used in program modeling and verification. So because it's very easy and natural to model sequential program using this kind of rules. For instance, you have procedure calls is just if I am in global state G and I have this L in my this is the local context in the top of the stack, then I can push this context maybe after some modification, and I will start the execution from some other context here, which is the called procedure and so on. So this is quite known, and it has been used by several people. Here I'm mentioning only this paper because here they use the approach we are using here in this talk. But basically a lot of work has been done using pushdown systems for sequential programs. And the reason why it's interesting is that there is a nice feature of these systems that you can compute the post-star and pre-star images. And these sets are regular. So if you start with a set of configuration, a configuration is a word, is the stack content. And if you consider a set, an infinite set of these configurations represented by an automaton, then you can compute the set of forward or backward reachable states. And this is, in fact, a very known old result, which has been discovered later in the context of model checking and has been improved from the point of complexity, and now it's implemented and used in tools. Now, when you go to parallel programs, so people tried to generalize this idea and this framework by allowing some parallelism. And the natural way to extend these push-down systems to have parallel programs is to use the so-called PA systems or process rewrite systems. So basically the idea is that you combine push-down rules with Petri nets, and you get a more powerful model where you can now model procedure calls and parallel process creation, still without synchronization in the case of process algebra. And this has been proposed by several people. And again, so let's see how, for instance, in PA systems you can model parallel programs. So you see that you have rules for sequential composition like this, and you have rules using parallel composition. Okay? So for instance, if I have this system, so you see that I can apply the rewrite rules like this. So I can, for instance, use this rule and get this configuration. And then I can apply here the rule Y to get something here. This means that Y has forked into two parallel processes. And then I will not rewrite Z before I finish this part. This means that I will apply some rules before getting this Z. Okay, so this is very simple. So yes, sure.
When, say, Y forks off into Y1 and Y2, two child processes, what information can Y send to Y1 and Y2? Is there a notion of like arguments or parameters or something?
Okay, in this case, no. I mean, it's only, so here it's only local variables. Now, if you have more general systems than PA, where you can have here control states also. So if you remember in push-down systems, you have two letters. So you have the control states and the local context. Then you go to somewhere else. Then you may have this value passing that you are saying. But not in this PA system. You have to go to some what is called PAD systems. But okay. So now, again, you have the analogous of this theorem for push-down systems for these PA systems, which has been shown by Luigi and Schnöbelen, saying that, again, you can compute the post-star and pre-star. Where here I am doing some simplification because in this theorem, you don't consider the fact that you have commutativity of the parallel composition. But in fact, it's enough to, even if you forget about this commutativity, it's enough to do, to apply this result for model checking. So I will not enter into these details, just to show you the picture. That's OK. So we have this PA process, and then Esparza and Podelsky applied this result to modeling, for modeling parallel programs. And it's also very simple, as you see. But here, what they do is that they model what's called parallel calls, or par begin, par end blocks. So you see that when you are in some location L, then you fork these two processes, and then you will not proceed until these two processes has finished. Okay? So this is this approach has been adopted by several people, and now the problem is that if you want to model spawn comments, which means that I spawn a process and I want to continue in parallel with my the child I have spawned. So you see, for instance, in this example, it's very simple. So you can start doing this, and then you call it yourself, and so on. And the other one, or you can spawn Y. Y has this behavior. So now you can see that, in fact, you will start doing these A's some number of times, and you are pushing B's in your stack. And then when you will spawn Y, you will start executing these B's in your stack in parallel with what this guy can do, which is this behavior, CMBN. So this is somehow the traces of X, the complete traces of X. Okay? Now, if you try to model it with these PA systems, you see that here, for instance, you will write these rules. And for instance, from N1, for modeling this spawn, you will say, OK, either I do M1, this one, or I will do it in parallel with N4. Okay? But the problem is that if you look at the behavior, you start from N1, you do A, and you go to N2, and then you go to N1, N3, because here you have some parallel, some procedure call, and so on. So you will generate this set of configurations, N1 with N3 to the N, and this is all the B's that you still have to do. Okay? And then this N1 will be transformed into M1 parallel with N4. But you see that now these B's will not be done before that this guy has finished, because of the semantics of this PA. And this means that it will generate this behavior, which is different from what we want. Okay? So in fact, this is not because I don't know how to model the spawn in this example with PA, because this is impossible to do it. You can prove that by some pumping argument that there is no PA system or PAD system, I mean, which can, in fact, generate this language. So this means that these models are too weak, or it's impossible to use them to really model programs with spawn comments. So in this talk, I will try to show you what we consider a natural model for these things. So this model is based on dynamic networks of pushdown systems, and I will show you how to do reachability analysis for it. And then I will try to extend it a little bit in order to generalize it, because in fact, this first one I will show you will not be able, for instance, to do this part begin, part end blocks that you have in PA. So now you can define something which will make the join between these two kind of models. It will be, it can model all these things, and also some other features like join operators and so on. And then I will show you that it's possible to do reachability analysis in this case, but using tree automata. And then if I have time, maybe I will talk about a more general model where you take this first one and you add asynchronous communication through shared variables. Then you get a model which is Turing powerful, but then we try to generalize this idea of bounded context reachability analysis that Shaz has with Jakob Rehoff, and this is a recent work with Sparsashvun and Strejček. Okay, so let's start with the first model. Very simple. You take the push-down rules, and now you consider that when a process can either, a process can either do a standard push-down rule, or it can do this push-down rule and spawn a new push-down system with control state P2, and W2 is the initial configuration. Okay, so this is kind of spawn operation.
Or the stack is
No. The gamma, W1 comes from instead of gamma.
Gamma and W2 is completely new?
This is new. This is what you create. Okay? So here the configuration now is something like that. Okay? So you have a sequence of contents of stacks. Okay? And then, so this is the semantics, the formal semantics. So you see now, so this is the standard one for pushdowns. And this one tells you that now if I have a configuration of this form where I see that there is a P gamma somewhere, then I replace this P gamma by PW1, but I create here P2W2, which is a new sequence, right? So it's always created to the left. Okay, so yes.
Why do you modify what's below in the stack? Is that because you have parallel processes?
No. No, the parallelism here is represented by the fact that you have several several configurations of pushdown systems. So imagine that you have a network of pushdown systems. Each one has, so his own control state and his stack contents, So here, in the same time, you modify your stack and you create a new one, okay?
So the thing is that all these control states at this joint
are
now visible only locally.
Right.
Yeah.
Yeah, that's true. So here, there is no communication. We will consider it later, okay? So we start from the very basic case. So now it's very easy to see that this example, well, it's, you can model it because here you just have this rule and it will give you precisely the behavior you are intending, okay? So I think it's not difficult to see it, okay? So then the first result we have is that, in fact, you can generalize these techniques for pushdown system to this model. It's not very difficult. So you can, if I take a regular set of configurations, okay, so I can compute the pre-star. So for that, you have to define some automata, which are in special form. So this is a picture showing you more or less the shape of this kind of automata. So basically, so you have states of this form from which you recognize, so you start with all so P1, Pn are the control state of your original system, okay, so those are the control states, right? So here, for instance, I recognize the fact that I have P1 and then I continue. Here I have P2 and then I continue. Then there are some states from which I jump from one process to another, the successor. This is an epsilon transition to another state of this form, and then I have this kind of things, and I may have loops. So you see that I can recognize any regular set of configurations. So any automaton can be transformed in this special form. In fact, it's not very difficult, okay? So it's just this special form is useful to apply this saturation constructions. So now what you do is that, okay, the first one is very easy. I mean, this is the standard pushdown saturation rule. So if you have this rule in your system, and if you have this path in your automaton, okay, so then you add SP to gamma. So you see here why the special form is important, because you assume that from this S, if I have P1 to some state, I have SP prime to SP prime for all the possible states, okay? So this comes from this form here. So you know that you have this. So what you do is that you can just add this from here. Okay, so that means that if you have a configuration here in the original language, okay, so this means that there is a path recognizing this configuration of this form. Now you know that this SP exists, so you just add this transition here to S prime, and then you create this new path which recognizes the configuration which is precisely the predecessor of the old one. So this is very easy, okay? Now you can do it for the other rule. It's the similar. So if you have this situation, so you will just create here SP somewhere here, gamma to S prime. Okay, so you can prove that this construction, it's not very difficult to prove that it's sound and complete. And you can even have this complexity. So if you, so this is the basic construction. Now you can have a more sophisticated algorithm where you use some memorization and so on, as in this paper, and you get this bound of complexity. So it's the same as for pushdown system, except that you have here +1. Okay, so you are multiplying by Q. Now what about forward reachability analysis? So in fact, that it's easy to see that post star of this doesn't preserve regularity. Okay, so this is a very simple. You consider only this rule. So what is this system is doing is that he is memorizing in his stack the number of processes he's creating. Okay? So then you get this set, which is context-free. Okay? Is it all right? So for this example, it's context-free. But in fact, you can show a general result saying that if you take any system and any context-free set, the post star is also context-free, and you can construct it. So now you are not working with regular systems, regular automata, but with context-free grammar or pushdown automata. Well, this is somehow okay, because if I have a context-free initial set C1 and the regular set, target set C2, I still can do something, because you know that all these operations are decidable. Right. Okay? So I don't know if I have to go to the details of this proof, but I will give you very short. I mean, the idea is just that you are constructing a grammar, which is very simple, in fact. You are just you want to construct the post star for every pair P gamma, and for every triple. For this, you construct the reachable state that okay, that will make your stack disappear. Anyway, so this is technical, but I mean, it's not very difficult to construct it, and you get a context-free grammar for these things, and then you can. So this is enough to construct the post star for a given configuration. Now, if you want to do it for a whole language, context-free language, you have to do some more work. You have to build a transducer and compute some context-free transaction. It gives you something which is of this size. Okay, so the conclusion is that even for this, okay, sorry.
Can you give us an example of when you start with a regular and ends up with a context free?
Well, the first simple example is,
So,
this one is, you see, you start from this configuration, which is finite, okay? And what you do is that the system is creating processes and at the same time is counting in his stack, okay?
So I don't understand why you cannot make it non-context free if you let also another spawn.
No, but they are nested. I mean, so another spawn. So, but you are doing it in some independent way. So you have concatenation of context. Yes. So because you are doing these things locally.
So you'll put them at the end?
Yeah, so assume, for instance, if I start from p gamma 1, p gamma 1, let's say, okay? So I will get two concatenation of the same language. But the concatenation of...
I thought about what happens if p gamma 2 will create also some gamma 3.
Yeah,
but then you will put it at the end.
Yeah, exactly, yes.
Thanks.
But this, for this you have to look at the rules. It will take some time to... It's not very difficult to... Okay, so you see, I mean, if you use this grammar here, for instance, let's say... I don't know. So, so I mean, if you generate this, you see if I have a rule of this form, let's say, so you see from this you will say next I will generate this context-free language, then I will concatenate it with this context-free language. You see, so it doesn't. Okay. And then, since I have sequences, so I have to have some transducer which reads a configuration and outputs these context-free languages. Okay, but this is possible because, again, you can make always this there is a push-down automaton which reads a symbol, start simulating the context-free language. When he will finish, he will continue. That's it. Okay. Okay, so now I try to generalize a little bit this model by allowing some kind of communication. Now you know that if I allow full communication, it will be indecidable. So what we try to investigate is this idea of having only one directional communication. So processes can talk to some processes, but the other ones cannot talk. They cannot answer somehow, so they cannot communicate this way. So there is a hierarchy between processes. And the hierarchy comes from the relations of, so a process can, for instance, watch his sons, the process that he has created, and can observe their states, okay? And he can take decisions from these observations. But his sons cannot observe him. Okay, so you have a tree now. So what we do, yes, sorry.
You mean like if P spawns P1 and P2,
yeah.
P1 spawns Q1 and Q2, then P can look at Q1 and Q2 also?
No, he can look at only his immediate sons,
right.
Yes. So here we generalize the model by just adding these constraints here. And this is a regular language over the set of control states. Okay, so because I have an arbitrary number of sons, so the constraints I will put is a regular language. Okay, so so let's see. What is the configuration is represented like this. So it's a tree. So you see here, this process has his control state P, and this is the stack. So it's represented in the reverse order somehow. So this is the top of the stack and so on from P. So this is the stack. And then he has his sons. And again, his first son has control state P1, and this is his stack, and so on. Okay? And you have an unbounded tree in the length and in the width. Okay? In the height and in the okay? So So what is the transition relation? So I'm just showing it in the picture, but I think it's simple to see, is that if I have this situation, the first rule, I mean, if I have a rule of this form, so I modify my stack. So this means that the first symbol here is gamma, then I replace it by this word. I take the reverse because of this representation I have, okay? And then here I modify it by p prime. And now this is done provided that these states, I mean this sequence of states here, is in the regular language specified by phi, okay? So that's the meaning of this rule, all right? Now if you add this spawn, so now it's the same, just that you add here a new son, okay? So this is the new control state, and this is the new stack contents. Okay, so you see that the number of sons can grow. Okay, so this is the semantics of this model. So this is just a formal definition of the same. So you have terms formally. So you are dealing with terms like trees, and so you can define this set and this. And then you can define this transition relation. But this is precisely what I have shown on pictures. Now, what can I do with these models? So, of course, I can do already the spawn, as in the previous one, without constraints. But now these constraints can allows me to do a little bit more. So, for instance, I can do this parallel, par begin, par end. So I can fork, I can have parallel calls, and then can wait until my sons finish to proceed. Okay? So for that, I will, so this is when I create these two processes, P and P prime. So if I am here, so assume that I have this transition in my control flow graph, for instance. So I start from here. So this sharp is just to say that the control state is not important here. So I'm just I'm going to some special symbol gamma 1 and spawning here, the first one, and then I spawn the second one. Okay, but I put this dollar at the end of the stack in order to say when they finish, they say it by putting this special symbol. And then, well, what I will check is that if there are two of the symbols at the end of the sequence, those are the youngest sons, they have finished, then I proceed to V. Okay? So I can do this. Now I can also model join statements. Assume that I have this spawn things, and then I want to say, okay, I will wait for some condition and then proceed. For instance, I have these things. So when I do the spawn, again, it's like here. I can always create processes, put this special symbol at the end, and when somebody terminates, he puts this special symbol in the sequence. And then I can model different kind of joins. For instance, if I want to say that if all my sons have finished, then I do this. So then it's just this regular language. If I want to say that there is K of my sons who has finished, I can say it like this. And you can imagine a lot of constraints of this form. Yes?
So what if, P creates a number of sons, but he wants to join on one of them? So, I mean, you have a way of identifying these various children by some kind of ID?
No, only by ordering. The ordering when I spawn them. Because the order...
How do I specify that I want to join on this guy? So for example, like the way fork join is implemented in actual code is that, when you fork, it returns an ID, a process identifier, and you can say join on that process. Can
well, we don't have an infinite number of symbols to do that. So, I mean, IDs, we cannot model them here.
But is there some indirect way of modeling that behavior or no? Maybe we can take it off.
Yeah, I mean, if you have a kind of abstractions on IDs, where you have only a finite number of IDs that you can do it, obviously. What you can do also is that you can remember the ordering. For instance, say if I spawn the first one, second one, and third one, I want to join with the second one, that I can do it because in my sequence, the ordering is memorized.
Okay.
But I'm not sure I can do. Okay. Now you can also have return values. You can say, okay, I spawn these guys, and then I will look at, again, for a finite number of possible return values. We can also have these things. Okay, so this shows that, at least for these models we had before, this is a more general model because it's extend them in several ways. And so it seems to us that at least it's more.
Sorry.
Yeah, sorry.
Could you just clarify one thing,
Yeah.
which is the regular expression is over the state of the immediate children.
Yes.
So the way you distinguish the state of the immediate children from the grandchildren is by using the tree language?
No. So this is in the semantics here. Okay. So you see here when you do this constraint here, talks only about this sequence of my sons, immediate sons. So you see,
So it's implicit in the semantics.
It's in the semantics.
Okay.
So it's you see, it's here.
But
if you have this and these states are in there, then you do this.
right. But the language that your process is generating will contain states of children and grandchildren at the same time.
Sorry.
So if you have a child process
Yeah.
that spawns another process,
Yeah.
your state of the system will contain.
You have the whole
states of both the children and grandchildren. However, your regular expressions will
Only about the first level.
yes. And the way you now, if the state were a string, it seems to be a little bit tricky to distinguish the state of children and grandchildren.
Well, the configuration is a tree.
Okay, it is a tree.
Yes.
So, but
But this is what I said in the beginning. This is the configuration. So the hierarchy is there.
okay.
So because if you want to flatten this into a sequence, it's I mean you will not get a regular language. I mean if I give you a regular language of trees and you flatten them, you will get a context-free because you have to put brackets to recognize. You know. Okay. Okay. So so that shows you the more or less what you can do with these constraints. It adds you some power. But now the problem, we have seen that forward reachability, even for the simplest system without constraints, is context-free. Now the problem is that even for backward, in this, if you have this general definition, it will not be regular. So this is a very simple example. What will happen is that, for instance, assume that you have two processes, and one will mimic, so that you have the father and the son. And the father is mimicking what the son is doing. In general, it's not the other way around, but here the father can watch his son, but not the other way. So each time the son can do something, so what he will do is he will decrease his stack. He just remove symbols. So from this situation, he will decide to remove a symbol. And then the other one, he say, this guy is in this state. Let's remove also a symbol from our stack. Then the other one move again to the other state where he can decrease his stack. And when the other one sees it, he will do the same. So if they keep do this, so of course what you can generate is that you can say that if you start from a situation, backward, where the two stacks are empty, you can say that the father cannot empty more than what the other guy has done. So you have always this constraint, n is less than m. Okay, so this shows you that you will get something non-regular again. And in fact, it's not due to stacks. You have two sources of complexity. Here you have two processes with two stacks, and they can do this behavior. Now, even if you have processes without stacks, you can do something similar if you allow dynamic creation. So then you will create a number of processes, and somehow they will simulate these two stacks. So you can do some move in one of them can do some move, and then information can propagate and go to the other ones and so on. And so you can encode again this. So maybe I will not go to this encoding. So this is the system which do that. So you see that from this situation, this guy can decide to go to P. Now this information has to propagate to this one. So they can do it using some rules here, because they can observe their context, their neighbors. So they can do it, okay? So the information can propagate here, and then this guy can modify his state, and then again, this one can change, and this information can again propagate, and you create something. And you see that you can keep playing this game, adding here something, and this guy can mimic it, okay? And so you will create, again, something which is non-regular. And even it will not be context-free. So it's a more difficult problem here. So it seems, well, for the moment, it's an open problem whether this model is decidable or not. I think yes, but what we do in order to be able to apply this saturation construction is to impose a stability condition. So what does it mean? So let's see. So if I have a language and a transition, so you say that this language is stable if when you move, you will stay in this language, okay, somehow. So, okay, so I have an alphabet sigma and a relation. So if I take a set of symbols, it's stable if whenever you move, you stay in the set. And now you can construct regular languages using this stable sets and these operations. Now what you can show is that if I take any language which is stable, then if I apply a transition in row, I stay in this language. Okay. So this is intuitively say that if you have one of these constraints, so even if you move forward, once they are true, they stay true. They will not become false again. For instance, when you have this termination, this is a stable property, okay? Because when you have terminated, you will not go back. So now you modify the definition by saying that phi is a row delta stable regular language, which means that row delta is the language between control state, which is defined by the rules of delta. So you can go from P to P prime if there is a rule of this form in delta. And for this model, so you can see that still all these examples I give you, they are all stable. So you can have this join, this termination, this parallel calls, everything can be, again, modeled this way. And you can also have something maybe interesting, which is observing execution phases. So you can consider that you have a process which will spawn a number of threads which will do some work, okay? And these processes go through several phases. Okay, so what you can see is that, okay, so you can observe the fact that some of them are in this or this phase. So for that, you will model these things using a hierarchy of control states. And you assume that the thread is in phase I if its control state is in pi minus 1. Okay, so when it will finish, it will be in pi. And this is somehow monotonic because you have these inclusions. So you can see that pi are stable states. And then, for instance, you can this father can test things like all workers' threads have finished phase I, or there is one of them who has finished phase I, and all the other ones have finished phase J. So all these kind of things that you can express using these phases with regular languages can be done like this. Okay, so this model still has some expressive power, and so we can prove that again we can compute the pre-star image of any set which is modeled by some kind of tree automata. But here, the tree automata we are using are called Hedge automata because we have these unbounded ranks. Because a process can have an arbitrary number of processes, right? So we have some kind of tree automata called Hedge automata, where to recognize sets of configuration, and we can again do the saturation construction. So what are the Hedge automata? They are very similar to tree automata, just that they have unbounded ranks. So basically what you have is rules of this form. So this kind of rules allows you to label the leaves of the tree, okay? And then you proceed from the bottom to the top, okay, using this kind of rules. So each time you have this rule, so you can label your tree. And then you have this kind of rules. They say that if my label is P, and if the sequence of states here is in the language L, then I can label the state by Q. Okay? So if this sequence is in L, then I put Q here. And then I can proceed. And when I reach the top, if the state I got here is in the set F, then I accept the tree. Okay? So this is the definition of the Hedge automata. And they have the nice properties that they have all, I mean, they are closed on their Boolean operation, and their emptiness problem and so on is decidable. And then we do the saturation construction. Okay, so so here it's the idea is like in the other cases, but here it's a little bit more tricky because you have to deal with these constraints and so on. So let's consider here you have these constraints. Okay, so this is just a push down rule, but you have to apply it on this automaton. So now if you have this rule in your automaton, and so this means that I can recognize trees, label them by some state Q1, Qn. Okay. Now if I also can have from Q, I have a word W to Q prime, okay, in this direction. Then, okay, this means that now what is the predecessor of this by this rule is that the P prime has to be modified to P, okay, and the W has to be modified to gamma. So I have to recognize now this one as a predecessor. So we have some special states here we have to add to the automaton, where you recognize all the states which have P in the roots and where the childs are in this language L intersected by phi, where phi is constraints in this system. So here we have to define this state, and there is a finite number of them. And you have to this, so the saturation gives you this. So the justification of this is somehow tricky because you have to show that stability allows you to do this and so on. So the proof is not so trivial, but basically, so the construction is this, and in the other case, it's something of the same form. So if you have in your automaton a rule of this form, and if you have this also possible in your automaton, this means that this is what, let's see, Q prime, oh, sorry, no, I'm talking about this one. So if you have these things, so this means that this is in your stack, and this is the sun you have created with the transition. Then if you move backward, so you will put gamma instead of this part in your word, and you will remove this sun. So this means that you take only the states, okay, and you get this part. Okay, so it's a little bit technical, but it's not very difficult. Now you can see that the number of states is exponential in this case in the number of all possible different constraints in your system. Okay? So somehow it's more complex in the previous case because you have this exponential. And in fact, you cannot avoid it because you can show that it's the problem is at least p-space hard. So to show, the reachability problem is p-space hard, and you can do it by reduction of QBF. So again, it's not very difficult. The idea is that you can, when you spawn, okay, for every variable you can choose a value true or false somehow. So you get a sequence of valuation, and then you check that for every clause, this valuation you have chosen is good. And for universal quantification, it's a little bit more complicated. But what the good news somehow is that if you fix the number of constraints in your system, the algorithm is polynomial. Because, so for instance, if you have a language where you have parallel calls, you have spawn operations, and you have a fixed number of join operators, for instance, for instance, you allow only these two ones, then the number of constraints is fixed and the complexity is then polynomial. So it's exponential only on the number of possible constraints that you can use. But if you fix them, so for every language with a fixed number of constraints, the complexity is polynomial.
But might it be the case that for such a case you would do it with usual tree automata?
Usual?
No, perhaps if you fix the number of constraints, then you don't need the whole machinery that you've developed, because then perhaps you could have calculated 3-star already with usual tree automata, because things would have been decidable. You won't have infinitely many.
Well, it's not the problem of tree automata. In fact, you can do the same construction even with the binary tree automata. It's not the problem of having, it's just simpler to express the construction with this hedge automata. The problem is to put these constraints or this sequence. Okay?
But you started because things turned out not to be context-free.
Yeah.
But perhaps in this case they will be context-free.
If you fix this.
Yes. And reduce the previous methods.
Well, it depends. If I take only these operators.
Yes, and then,
right.
And then you know it's
in that case, yes, exactly.
Because previous method.
Yeah. Well, anyway, if you take these if you take these operators, you know that it will be regular, and the fact that we represent them by hedge automata is just it simplifies things, but it doesn't. So
what I say is that I guess that you had the polynomial complexity already from previous methods, because.
Which methods? I don't know.
Well, may I interrupt this? Take this offline?
Yes.
Yeah. Okay. So. Okay. So how much time do I have?
Well, since we started late because of the interruption.
Okay.
Can you wrap up in like 5-6 minutes?
Yeah, I will just mention this and stop. Okay. So we have seen two models. This basic one, this dynamic push-down networks, right? Without any communication. We have extended it a little bit with these constraints. And now, if you come back to this dynamic push-down networks, and you add communication, asynchronous communication with global variables. Okay. So what we do here is that you have a set of global states, you have a set of local states for every process, and you have two sets of rules, locals and global ones. So the local ones are as in DPN. Okay, so you have either push-down rules or push-down with spawn. Okay. Now this global ones says what? I am a process. I can look at the global state, which is shared by everybody, and I can now move this way. So I can modify the global state and in the same time do some local changes. Okay? So we have these two kind of rules. Now, is it clear? Right? So now, what's, well, it's very simple to see that it's Turing powerful. And now what we can do, what we have done is that we have adapted this idea of bounded context reachability. So here what we define as a context is a transition sequence where global transitions, the global are performed by the same component. So you can see that in this definition, so only one can use global states, but the other ones can do local moves. So they have their own control state and they can do these local moves without any restrictions. So somehow it's different from the definition in the paper of Shaz and Jacob, because here you can have an unbounded sequence of local moves within one context. Okay. So it's you see that it's a very natural generalization of the previous model. So okay. So if you want, I can tell you about this, but so I just mentioned that we can prove these two things. So you can do bounded context reachability analysis forward and backward. So for backward, so you basically will repeat k times this pre-star construction. Okay, we have seen. For forward, it's a little bit more complicated because you have to, again, to iterate, but if you do it, you will get a high complexity. So what we do is that we reduce the problem to only one context-free grammar, and so we can build one context-free directly for this. Okay, so technically I can maybe...
Basically the results from the case when you did not have the global state just carry over.
Right.
For pre-star you have regular sets, and for post-star you have context.
Exactly, exactly. So you have just to do some tricks to adapt this, to incorporate the global states and so on and so on. So technically, if somebody is interested, I can show, but okay, so that's all. So okay, as a conclusion, so we have proposed these models, and we hope that they are natural models for multi-threaded programs, and they are decidable. And we have extended these automata-based techniques for this kind of models. And the complexity is polynomial if you fix the number of constraints. And it's an observation is that in this case, that forward analysis is always more complicated, more difficult than backward. For the ADPN extension, so we have generalized this bounded context reachability analysis for this case. And in fact, it could be also done for this CDPN, this other model where you add this. It's the same stuff, but you will use, in that case, three automata instead. So there are some open problems. Of course, the CDPN model without stability condition. So we think that it's decidable, but for the moment, I cannot say it for sure. And also forward analysis for this CDPN, it's not done. Because we have seen that forward for DPN, it can be done, but you use context-free languages. But here, it's more complicated because you have trees, so you have to design some kind of push-down tree automata for that. It's very tricky. And we are also trying to do, because this gives you somehow, this bounded context reachability analysis gives you somehow lower approximations of your set of reachability states. But if you want upper approximations, so that's you have to use some other approach. And the one we are trying to use is abstract regular model checking. So this is something that we have introduced here with these people. Basically, it's a generic framework where you have automata representations, and you compute backward or forward using transducers. And we have some abstractions on the automata representations, which allows you to have upper approximations on the set of reachable states. And this has been applied for various kinds of infinite state systems, in particular for programs with pointers, in very restricted case, of course. And here it's something that can be, this framework can be adapted to here to this very easy. So we can use this. So we can have two methods for upper approximation and lower approximations, maybe. Okay, so that's it. Thank you.
Feel free to continue question and discussion in case you want.